Hello everyone, my name is Syed Bari. I'm a PhD student in CPES Virginia Tech, and today I'm going to talk about my research work about transient performance improvement in constant on-time control. The title of this work is Transient Performance Improvement for Constant On-Time Control. Here in the left side, you can see the constant on-time control structure. Today, constant on-time control is popularly used in the industry for better light load efficiency and high bandwidth design capability. However, constant on-time control still has some limitations in load step up and load step down transient responses. We know that in the constant on-time control, when inductor current touches Vc, a fixed on-time pulse is initiated and at the on-time IL increases. After that, IL starts decreasing, and when touches Vc again, a new pulse is initiated again. In the load step up transient, when Vout falls, then Vc rises and hence increase the duty cycle to increase the inductor current. But if the load step is very large and quick, then the Vout falls and Vc rises very quickly. As a result, IL cannot follow and the Vc and then duty cycle saturates. At this point, the series of pulses comes in, but in that case, they must have a minimum of time in between the on-time pulses. The presence of this minimum of time will slow down the increment of inductor current, which might create a large undershoot at the output. On the other hand, when load step down occurs, if load release is occurred at the beginning of the T-on, inductor current is expected to start decreasing right at this point. But because of the fixed T-on time, IL keeps increasing till the on-time expires, and this inductor energy, extra energy, will be dumped at the output capacitor, and hence it might create a large overshoot. Let's look at the issue very carefully. Here at the load step up, when load rises quickly and IL is trying to catch up, if we look at the output capacitor, it is discharging and output is falling down. After the point they become equal, the IL becomes higher and the output is going back to the regulation point. Now we can understand very clearly that if we want to reduce the undershoot, we have to increase the IL increment slope in this yellow region. To do that, we can increase the on time in this region, and also very importantly, we don't want to increase after this point, which is in the blue region, to avoid any chance of overcorrection or ringback problem. Now to achieve that, we propose a method called fast adaptive on time, fast AOT, which sends the derivative of the output and use it to increase the on time at the load step up transient. The benefit is very clear. No threshold required to detect the undershoot, eliminate any chance of ringback of V out, and this T-on extension is adaptive. On the other hand, when V out overshoot occurs at the load step down, this DVDT can immediately goes low, and that can be used to truncate the T-on pulse, which will make the IL reduce immediately and reduce the overshoot at the output eventually. Now let's look at the possible implementation of the proposed fast adaptive on-time concept. For the implementation of the proposed concept, we start with a conventional adaptive on-time control where Vin and Vref are sensed by the T-on generator block to keep the frequency variation under control. First, we take the Vout and use a bandpass filter to detect the undershoot or overshoot at the output. The reference is used to add as a DC offset, and the bandpass filter passes only the high frequency part of the undershoot to the output VFLT. But the output VFLT contains some ripples as well. which comes from the DVDT of the output ripple, and that might create the jittering at the steady state. Therefore, in the next stage, a very simple emitter follower is used to block the high frequency switching ripple at VFLT. In this way, only the peak is created in the VFLT by V out undershoot will pass through this stage, will be seen in the VFOT node. When VFOT is used as a reference for the T-on generator circuit inside the green box, the peak at the VFOT will increase the T-on according to the undershoot magnitude. Here the point is to be noted, there's no perturbation injected in the steady state, and after the T-on extension, the extension reduces gradually, which actually eliminates the chance of the overcorrection and undershoots. In case of load step down, when the bandpass filter is proposed circuit detects any overshoot at the output of the converter, the bandpass filter output VFLT goes down very quickly. Then this signal is compared with 80% of VREF to generate logic VOS, which eventually ended with the T-on to expire the T-on immediately and reduce the overshoot at the output. Now here you can see that we try to implement our proposed fast adaptive on-time circuit with TPS 59650 evaluation board, and in the first single phase we reduced 50 millivolt undershoot to 42 millivolt undershoot, and in the two-phase operation you can see from 105 millivolt to 90 millivolt by extending the T-on. Here we propose another implementation of our proposed concept. In this second implementation is of proposed fast adaptive on-time control, we use current instead of voltage to change T-on. In this case, we use the filter output to convert into current by two GM amplifiers. In the load step up case, we subtract some current from VC node, will make the V cap ramp flatter and make the T-on longer. In the other case, we add more current into the V cap node to increase the ramp to reduce the T-on. The advantage of this method is we can set GM of these two amplifiers separately according to our requirements. Now we have the method 1 and method 2, and let's look at the key features very quickly at the end of this presentation. The key features: both undershoot and overshoot can be reduced by using one single circuit. We don't need any threshold detection, no overcorrection or ringback problem, and no impact on the constant on-time loop at the steady state. And this is very easily implementable with the state-of-art all kinds of adaptive on-time control using PLL or using V in, V out sense. And as the gain of the filter we can change very easily, this is very easily tunable. So thank you very much. This is a TPS 59650, a three-phase VR board, and we try to implement our proposed control method with this board to show that the proposed concept can improve the transient performance. The left side you can see the small part which actually added with this board to improve the performance of the control method. Here in this board, in the constant on-time control and single phase operation, you can see in the load step up transient response, the pulses come very close, and we actually reduce some output capacitor in the board. For that reduced number of cap, we can see some undershoot here at the output. Here now you can see the same setup and the same load transient response. Only difference is that we introduce our proposed control with the constant on-time control. And to show the load transient response, you can see that when this on time is extended using the proposed concept, the undershoot actually is much less than the previous picture. So that's how we can increase the on time and improve the transient performance of the constant on time control. Here in this picture, we want to show you the setup for two-phase operation, you can see that in the load step-up transient you have several pulses of phase 1 and several pulses of phase 2, and still you have some undershoot at the output. Now here the same two-phase operation with our proposed fast adaptive on-time control method, you can see we are being able to extend this on time, and for this we can achieve the reduced undershoot, which is now 90 millivolt, and the previous case without the proposed concept it was 105 millivolt. So we have been able to reduce the 15 millivolt of the undershoot in this case. That's all about my presentation. Thank you very much.